Good morning, everyone. My name is Zavia Esra, roll number 24951A12CA from Information Technology branch. Today, I'll be presenting on error control coding ensuring reliable communication in language. Course first name is Computer System Architecture. Course code is ABCD04. This topic is about bridging the gap between raw data and flawless information delivery. In other words, how we make sure the information we send arrives exactly as intended despite errors caused by noise in communication system. The challenge. The challenge in error in digital communication. In our digital world, data travels through different mediums, wireless signals, optics, and even storage devices like hard drives. But no medium is perfect. They are all vulnerable to noise. Noise can flip a single bit, turning 0 into a 1 or 1 into a 0. This might small sound, but it can lead to major consequences like a drop video call or corrupted file or unreadable sector on disk. Without protection, data integrity would constantly be at risk, making reliable communication almost impossible. This is where error control coding comes into play. What is error control coding? Error control coding or ECC is a safeguard that adds redundancy to data before transmission or storage. This redundancy isn't random, it's mathematically structured so that the receiver can detect and even correct errors. The key metric here is to code rate. The key metric here is to code rate, which is the ratio of useful data to total transmitted data. A higher code rate means efficiency but less error protection. A lower code rate means stronger protection but more bandwidth usage. ECC or error control coding strikes a balance between reliability and efficiency. Two main approaches. There are two broad streams, error detection and error correction. Error control coding broadly categorizes into two primary strategies, each serving a distinct purpose in ensuring data integrity. Error detection. This approach focuses solely on identifying whether errors have occurred during transmission or shortage. The receiver knows if the data is corrupted but cannot fix it. If an error is detected, a retransmission request, automatic request, or ARQ is typically sent. Common example includes parity check, a single bit added to a block of data to make the total number of one as either even or odd. Cyclic redundancy check, a more powerful method for polynomial division widely used for data integrity in networks and storage devices. Error correction, also known as forward error correction. This method is a step further. It adds enough redundancy to the data such that the receiver can not only detect errors but automatically correct them without the need of retransmission. This is vital in scenarios where retransmission is impractical or impossible, such as satellite communication. High latency makes retransmission insufficient. Broad media, no return channel for retransmission requests. Data storage enables recovery of corrupted files. This is a very essential scenario where retransmission is costly or impossible. Both strategies ensure data integrity, but the choice depends on the application. Types of codes. Block versus convolutional. Error control code can be broadly categorized as block codes or convolutional codes. Block codes divide data into fixed size blocks and each block is encoded independently. Example including Hamming codes or Red Solomon codes. These are usually used in storage systems. Convolutional codes work continuously where the current output depends on both current and previous input bits. This gives them memory and stronger gives them memory and stronger error correction capabilities. They are widely used in wireless communication like GSM and Wi-Fi. Classic example: Hamming code. One of the most simplest example is and the most famous example is the Hamming 744. It takes 7 data bits and adds three. It takes 4 data bits three and add three parity bits to form a 7-bit code word. It can detect up to 2-bit errors and correct any single bit error. This is possible because of the hamstring distance, which is the minimum number of bits by which valid code words differ. In this case, it's 3. Making correction possible, hamstring codes laid the foundation for more advanced codes that are still used today in ACC RAM and memory system. So, hamstring 74 is one of the most simplest yet illustrative examples of perfect error correct code. Encoding: for every 4 bits D1, D2, D3, D4, there is a 3 parity bits P1, P2, and P3 that are generated based on specific combinations of data bits. These are interleaved to the form 7-bit code word. Detection and correction: the magic of hamstring code lies in their ability to detect up to 2-bit errors and contact any single bit error within their 7-bit code word. This is achieved by calculating syndrome bits at receiver, which pinpoint the exact location of the error if one occurs. Hamstring distance: the code is designed such that any two valid code words differ by at least 3 bits. The separation allows the receiver to determine the most likely original code word even if the bits are flipped by noise. Efficient algebraic codes. Another powerful family is cyclic codes. They are special because if you take a valid code word and shift it, the cyclic, you'll still get another valid code word. They are often represented with polynomials, making encoding and decoding efficient using shift registers. The strength is in the strength is in handling burst errors that affect multiple consecutive bits. Applications include CD, DVD players, internet CRC checks, telecommunication systems. Their efficiency and algebraic structures make them widely used in digital systems. Modern powerhouse: low density parity check (LDPC) codes. Moving to the modern coding, low density parity check codes, they were invented in 1960s but became practical in the late 1990s thanks to improved decoding algorithms. LDPC codes use pair parity check matrices which enables efficient iterative decoding. They achieve performance very close to Shannon limit, meaning meaning near optimal reliability. They are now the backbone of modern high-through output system used in solid-state drives, 5G wireless communication, Wi-Fi 6, digital video broadcasting. LDVC represents the cutting edge of error correction today. Real world application: error coding isn't theoretical, it's everywhere in our life. Data storage, wireless communication, satellite communication, digital broadcasting. Error control coding isn't theoretical. We use ECC in data storage. HDDs and SDDs rely on ECC to recover from bit errors and extended device lifespan. Wi-Fi, 4G, and 5G uses ECC to deliver clear calls. Deep space missions, GPS, TV broadcast all depend on EFEC. Challenges of trade-offs. While ECC is powerful, it comes with a trade-off, such as bandwidth overhead, complexity, latency. Adding redundancy meaning sending more bits consuming extra bandwidth. Computational complexity. Encoding and especially decoding require heavy processing, impacting device power and speed. The processes introduce delays which matter in real-time apps like live calls or autonomous vehicles. The challenge is balancing these. To conclude, error control coding is the silent guardian of digital age. It transforms unreliable, noisy channels into robust and trustworthy communication links. From storing photos on your phones to making an international call to streaming 4K videos, ECC ensure your data arrives safely and intact. As we push towards faster networks and higher data demands, ECC will only grow in importance. Understanding these codes empowers us to design technologies that are faster, more reliable, and future ready. Thank you for your attention.